Good evening to all professors. It is my pleasure to welcome you all to this fifth day first session on emerging renewable energy technologies. Today's speaker, my senior from MIT, Mr. Ilongovan Ramasuppu, working in Emerson, Manager Natural Gas System, Singapore. Welcome you all. Welcome you, sir, for this wonderful gathering. As we gather here today, the world is at a critical juncture into its energy landscape. The pressing need to address climate change, energy security, and sustainability has brought renewable energy to the forefront. Our expert speakers, Mr. Ilongovan sir, will deliver into the latest advancement challenges and opportunities in this field. I would like to extend my gratitude to our esteemed speaker for their contribution to this program. Let us work together to harness the power of emerging renewable energy technologies and create a sustainable future for all. Thank you, and let us begin with this exciting journey of learning and exploration. I will call upon Dr. K. Purushothaman sir, co-coordinator, to give detailed introduction about Mr. Ramasuppu Ilangovan sir. Ilangovan Ramasuppu sir, please sir.
Thank you, Dr. CHINNAPANDIAN sir. The first would like to express our sincere thanks to the organizer to give me the opportunity to introduce our chief guest, today's speaker, Mr. Ilangovan Ramasuppu. I welcome you, sir, first of all, and also welcome you all the participants. We are conducting the 6 days FDP program sponsored by AICT and supporting with our management, St. Peter's College of Engineering and Technology, and organized by Department of Mechanical Engineering with coordinating with Dr. Chinnapandian and myself. Thank you for accepting our invitation to going to deliver your knowledge for our faculty members. Thank you once again, sir, and also I welcome you, sir. This is the title of FDP is Energy Conservation and Storage Technologies for Global Sustainable Developments. So our speaker also is going to give related to our topic, most relevant topics. Almost all the speakers last 4 days, they are sharing their knowledge. I think we are expecting today also because of the guest is having more than 45 years of experience in this field, and he has completed BSc Mathematics in ANJA College, Sivagasi in the year of 1976. And in the year of 1979, he has completed BTech in Instrumentation from MIT Anna University, Krompet, Chennai. So he's having 45 years of experience in the process control and instrumentation field. And also he's worked October 2024 to till date, a full-time consultant at Emerson in Singapore for developing in-house training program. And also is have experience in this January 1998 to September 2024, worked at Emerson in Singapore, did many roles in sales, marketing, business development, application engineering, training, and profit and loss management, and retired on 30th September 2024 as marketing manager for natural gas system. And also is having work experience from January 1989 to January 98, sales and application engineer for pressure control valves business in Saudi Arabia. And also from August 1979 to January 1989, the instrument engineer at SPIC fertilizer plant in Tuticorin, Tamil Nadu in India. And also his expertise in these different areas, control valves and their applications in process industries, self-acting pressure regulating valves and their application in process industries, and natural gas instrumentation and distribution network, and also natural gas transmission and distribution system solutions, fuel gas supply system to power and cogeneration plants, gas gas conditioning system solutions, and also decarbonization solution involving hydrogen and biomethanes. And his interest is to sharing the knowledge to the societies and technical consultancy and training the peoples, okay, for in experts, and also traveling in all over world. So I welcome you, sir, once again, and really happy to be here in our FDP program, and we are going to gain experience from your insights, sir. Thank you very much once again. I welcome you, sir, and also welcome you all the participants for this fifth day first session FDP program. Thank you very much, sir.
Can you hear me, and can you also see my slides in the full screen?
Absolutely,
Yes,
sir.
sir.
Everything
Yes,
is
sir.
okay.
Yes, thank you.
Yes, sir. Yes,
Okay,
sir.
thank you. Okay, so thank you for the organizers to give me this opportunity. I have done many training programs, even done some guest lecturing in colleges, universities in India. But this is the very first time that I'm actually speaking to an audience full of academics, many scholars, doctorates. Previously, when I did guest lecture, I probably spoke to, the final year or the pre-final year graduate students, but never before had I spoken to an audience of this nature. So it's a great honor for me. And, thank you, Mr. Dr. Purushothaman, for excellent introduction. So, I believe, many of us are able to grasp things in an audio visual form. When we see something and then there is also an audio describing what we see, then I think our understanding level goes higher. So with that in mind, I actually put a slide about myself. You see my photograph there. I do a lot of training. I did a lot of training in my work environment. So there's one of those photographs that you see there. It was done last year, 2024, product training for our salespeople. Yes, I like travel, and the photograph that you see on the left bottom corner is a picture of me and my wife standing on top of a glacier in the southern island of New Zealand. Last April, we were there for a holiday. We took a helicopter ride from the shore to the top of the glacier, which is kind of on the mountain, and then we had that experience. And then there is one other picture that is to the bottom middle, showing a starfish. I like to help people in financially needy people. So I have done some work in that area, help some people to complete their education programs. So some of you may have heard about this starfish story. A lot of starfishes are found on the sea beach, and then there's a boy who is picking up each starfish and trying to throw it into the water back again. An elderly person walks by and he says to this boy, hey, there are so many starfishes, and you're just one of you. What's the point in throwing a few back to the sea? And the boy replies saying, it doesn't really matter, but it matters to that one starfish that I threw back. I may not be able to save every starfish which is on the beach, but if I throw one back, at least that one starfish will go alive. So I believe in that, and I've been trying to do something around that throughout my life. Okay, so that's my kind of introduction. So this page, are you able to see my page? Is the slide number 3?
Okay, sir. Okay.
Okay, yeah. So I really want to put up this disclaimer because, the speakers earlier in this program, they're either from research background or from companies that they've done some research. Like yesterday, we had a speaker from Reliance, So he's really working on a project that, is working on hydrogen-based vehicles and stuff like that, right? So I'm not a scholar. I didn't do any, research and development program. And I worked in sales, I worked in marketing, and I run some business, within the company, a small, business. took a P&L responsibility for it and stuff like that. So whatever I'm presenting here is based on my own acquired knowledge in my work and other learning processes. And then, if I say something, it doesn't mean that neither my, past employers or present employers, they all agree to what I say, so, they should not be held liable for what I say. So that's the disclaimer I'm trying to put it here. Because I just retired from an American company and I'm back to the same company as a consultant through a third party. I'm no longer an employee of that company, but I'm an external consultant for them. So having worked in an American company, I'm supposed to abide by some of the American rules and regulations. So that's why I need to be very specific about this one. And during my presentation, you'll find that I do mention about certain products. You'll see some photographs and pictures and stuff like that. So that does not mean that those product owners, manufacturers, they have any specific recommendations for this one. It's all my own understanding of the product, how they work and stuff like that, and I'm presenting it here. Okay, so they cannot be held liable for that. And again, I just need to make sure that if there is anything inaccurate in what I say, it is purely my own view, my own opinion. Nothing to do with the present past employers or the trade name owners and trademark stuff like that. Okay, so in this session I'm going to be covering these 4 things. Why renewable energy? Many speakers before me have addressed that, so I won't dwell too much on it, but touch briefly on it. And what are the drivers that I see in the market, in the industry, that is driving this renewable energy, and what are the challenges and opportunities. And in the opportunities, I'm trying to express my view on what is in it for academics and research scholars like yourselves. Okay, so just a quick recap on what is natural resources. It's a very pictorial, so you can see it for yourself. Water, sunlight, soil, animals, and then plus we also have energy intensive materials like crude oil, coal, natural gas, precious metals, that can be used for energy, intensive actions, things like that. So these are the natural resources that we have around us in this globe. And amongst this one, some are renewable. We have been using the other ones like hydropower, solar power, in a small way. But our primary usage has been on the non-renewable energy. And we have found that even though we only use it for the last 100 plus years, and many are not renewable. Okay, so it's a very simple chart. On the left, you can see, sun, solar energy, water, hydropower, geothermal energy. A lot of countries around the world have the privilege of using geothermal energy to harness, their electricity. Wind energy, most countries have that as well. And of course, there is another one called biomass, So these are all renewable. So these have been there forever, ever since, the universe, existed, Mother Earth existed. These things have been around. But we also found non-renewable energy sources like fossil fuels, coal, natural gas, all these things, are also available in Mother Earth. And then currently, the last maybe 100 years, we have been using these non-renewable energy sources as the prime energy source. It has caused severe damage to our environment. We feel the pinch of it. We feel the global warming, because of that. So scientists and academics like yourselves, research scholars like yourselves, have identified the actual reason why the environment is getting worse and the global warming is occurring. It is for real. So it is all affirmed with people like yourselves. So based on that, the entire global community is now gearing up to reverse the process. That means, can we stop using these fossil fuels? Not immediately. It is not like on-off switch. We can't do that. Over a period of time, can we transition from this non-renewable energy to the renewable energy? And that is the discussion we are having today. Okay. So here's again another quick chart, to tell what are those non-renewable fossil fuels and how they help and So one of the thing is the fossil fuels are in a limited quantity. We know they took millions of years to form under the ground, whether it is a coal, oil, natural gas, whatever. They all took millions of years, and then, all the vegetation that existed millions of years ago, they got buried underneath, and then they converted themselves into these hydrocarbons, and they're extracting them from very deep, underneath this, Earth's surface, and then using it. And then going by the, statistics that are available, they say the oil will only last for the next 50 years. The gas will last only for next 70 years if we continue to use in the current rate. If we increase the usage, the number of years will even come down. So this is the actual situation. So what are we going to leave behind for our grandchildren, grandchildren, and their grandchildren? What are we going to do? Within the span of 100 plus years, we have consumed so much. And then even the coal, they say it can only last for next 250 years. But we all know that this Mother Earth is going to exist longer than that. And therefore, it is the reason why, the first question of why renewable energy is answered by these few slides that we just now saw. Okay. And the catastrophic, things that we see, unpredictable weather patterns, I was in Texas a few years ago in the month of May in the US. In the month of May, Texas is the southern part of America. There was a snow, unpredictable. And this all, people say it is because of this weather pattern, right? The change in weather pattern. Okay. So I think this topic has been touched by previous speakers as well, but I got a slide to kind of, make it a little bit more clearer. Okay. So greenhouse gases do exist in nature. We didn't introduce it. We didn't introduce everything. Even before these fossil fuels were used, these greenhouse gases were existing. We breathe out carbon dioxide, right? But plants breathe in carbon dioxide for the photosynthesis. So there was a balance, right? So there was carbon dioxide existing in the, there was moisture in the atmosphere. There was a methane. Any biodegradable material, food waste, dead animals, dead wood, when they decompose, methane, CH4, is one of the constituents that is released from the decomposed material. Okay, so all these things were being released into atmosphere, and they were in the atmosphere, and they were actually providing a screening. When the solar radiation arrives to the Mother Earth, these greenhouse gases were actually helping to reflect some of those energies, so they don't reach the Earth. So there was a balance. There was a balance available, prior to this industrialization. But what happened now was, when we started to use these fossil fuels, we are adding tremendous amount of carbon dioxide into atmosphere. Plus, just not carbon dioxide. The greenhouse is just not carbon dioxide. Carbon dioxide is probably the major constituent, but there are others like, the NOxes, as we call them, right? Nitrogen oxides. Okay. So those are equally harmful. And then one thing that will come up in next slide is this is the effect of what happens when we release 1 kilogram of carbon dioxide or 1 kilogram of methane or 1 kilogram of nitrous oxide or 1 kilogram, the fluorinated gases, as we call them, right? As you can see, if we release 1 kilogram of carbon dioxide and the effect is say 1. If I release 1 kilogram of methane into atmosphere, the effect is 30 times. So that means, if I release 1 kilogram of methane, it is equivalent to releasing 30 kilogram of carbon dioxide. It is so much bad. So we all talk about, when we talk about carbon footprint, the first thing that comes to our mind is carbon dioxide. But there is more than carbon dioxide. Methane is more harmful. If I release 1 kilogram of methane into atmosphere, it is more harmful than releasing 1 kilogram of carbon dioxide. Nitrous oxide, even worse, 300 times. That's why, the emission regulation is, we can only release in ppm level, nitrous oxides. And fluorinated gases, we were using fluorinated gases in many applications, aerosols and, refrigerations, we have been using all these gases. And then we now realize that thousands and 10,000 effect, that they affect. Now, if I release 1 kilogram of the fluorinated gases, it is equivalent to either 1,000 times releasing a 1,000 kilogram of carbon dioxide or 10,000 kilogram of carbon dioxide. But again, on the right-hand side, you see, that every human, living on this Mother Earth is contributing to releasing 76%, carbon dioxide, 16% methane. But the 16% methane, if I multiply 30 times, it is more harmful than 76% carbon dioxide release. And you may ask me, hey, how is a human releasing methane into atmosphere? I'll give you an example. Before KFC, McDonald's, all these fast food chains came on board, the consumption of beef was not this high. But now, beef consumption has skyrocketed around the globe. And you know how this beef is now provided? There are cattle farmed just for meat. These cows, when they digest their food, they release methane. That means the population of the cows, cattle, grown just for providing beef to the entire world has quadrupled. It has multiplied many times. So every consumption that we have impacts methane release into atmosphere. That's how bad. Nitrous oxide, today, you can imagine 10 years ago, how many cars were there in Indian roads? How many cars are there today? And how many cars are projected in the next 10 years? And every emission coming out of the tailpipe has got nitrous oxide in it. Okay, so we are increasing. So everywhere we burn something, there is a release of nitrous oxide, carbon dioxide. But methane is different, So here is a chart. It's a busy chart, I know, but I don't expect you to read everything there. But I just put some highlights there, On the top left-hand corner, what you see there is, the total investment globally exceeded $3 trillion. Okay, I hope you understand. Trillion is around 10 to the power 9, for the first time in 2024. And out of that, 2 trillion went to clean energy technology infrastructure. Just to give you an outlook, how much of investment is pouring into that area because of the climate change conversation that is taking place around the globe. A lot of people are committing to do something to reverse this situation. So there is a lot of money invested in the clean energy technologies and building the infrastructure. Like yesterday, we were talking about, Reliance spending money, to develop clean energy, infrastructures, including, hydrogen refilling stations and stuff like that, right? So all of that is included there. And this report is all coming from, a very reputed agency called International Energy Agency. So none of it is mine. And then you can see, right in the middle is India there, so India is not, equivalent to like US or China, EU at the moment, but at least, we have a commitment from the government to do that. And then to the top right, you see, it's all like, people in the, India is, you can see that, double the clean energy investment by 2030 worldwide. Many countries have committed to that, and in the emerging market and developing nations, developing, EMDE, there it is even quadruple. They want to, 4 times they want to go up. Okay? There's a commitment people are giving. Okay, and you can see, where they invest. The conventional one, and the clean fuels. So all of that. On the bottom left, you can see, again, different countries. India is there. The light blue is India. Okay, where you can see, infrastructure investment happening, across the globe, and India is right there, number 5. And then, to the right, just a snapshot of, people talked about solar, energy harnessing. We talked about photovoltaic, the solar panel investment. The solar panel in the last 2 years, have dropped. The cost has dropped by 30%. But yet, you can see the investment from 2021, 2022. You can see, steady increase. That that orange bar has gone up. So the investment in solar panel installation has gone up so much. At the same time, the solar panel cost have dropped, which means, more than 30% growth in the installation. So these are all the scenarios that we are experiencing in the investment investment in the renewable energy. Okay. So this is another busy chart, showing the renewable energy landscape. If you walk from left to right, on your screen, so on the left, you got the fossil fuels, which is not the renewable energy, but you see the hydro, the nuclear, solar, wind, they're all the, renewable energies, and then we also have like a coal and biomass, we also have natural gas, all these things combined. Okay. My topic today is going to be more on the 2 things that are circled in red, hydrogen and biomethane. It doesn't mean that others are, less important, but, my expertise, my focus in my job in Emerson has been around these 2, and therefore it is best for me to share what I learned in my job, around these 2 products. Okay. So there you can see the hydrogen is used, in many applications. Let me just take you to another page here. Hydrogen value chain. Okay, from the way it is being produced, how it is stored and transported, and how it is utilized. Okay, so this is a very simple chart, as you can see. So hydrogen is not something totally new. So maybe I'll take you to one other page first and come back to this page. Okay. Okay. This is hydrogen facts. I just did some, research on this information, and I compiled this one for my internal training, and I'm going to use it here as well. Hydrogen was first produced accidentally in 1671. 400 years ago, 350 years ago. Okay. And then it was recognized as an element in 1766. Okay. So, I'll skip all of that. Okay. But then you can see, hydrogen fuel cell was built in 1842, not today. We are using that in a very commercial way today, but the first hydrogen fuel cell was developed and built in 1842, almost like, 170 years ago. A hydrogen fueled internal combustion engine was built in 1806. But today we are trying to refine it, make it more commercially viable. But somebody built an internal combustion engine for hydrogen so long ago. And then hydrogen balloon was built in 1783. You see a picture there. Okay. So it's not something, and hydrogen was liquefied in 1898. Hydrogen was solidified the next year. And then, hydrogen has been used in refining, petroleum refining, for donkey years, I would say. And then another one, 1901, hydrogenation of vegetable oils. I know that in India, we have a product called dalda. I'm not sure if it's still available or not. Hydrogenated, fatty acid, is an alternative for like, the butter, right? People use the dalda. It is actually unhealthy food, but we have been using it. It's not new. So hydrogen is nothing new. And then you see the next one, 1938, in Germany, they commissioned a 240-kilometer hydrogen pipeline and still working. And then, of course, the liquid night hydrogen has been used as a fuel for rockets, by NASA in the USA, and many other countries are using it now, And therefore, in 1970s, the hydrogen usage in refineries, in petrochemicals, in metal, in the foundries, steel and stainless steel foundries, they've been in use. So it's nothing new. But what happened was there was a cautionary approach. Okay, there was an incident, as you can see there, Hindenburg, right in the middle column there. It is an airship. This was an airship. People were traveling by hydrogen-filled airship between continents, between Europe and America. There were many flights before that May 6, 1937. But in May 6, 1937, a flight that originated from USA, destination Europe, midway, it met with an accident and everybody on board was killed. And then immediately after that, they banned airship using hydrogen. Okay, so that was one incident that stopped hydrogen airship, and never done after that. So that's what, and then there has been industry accidents, like with any other chemical or a hydrocarbon, there has been industry accidents involving hydrogen. And they're all primarily because equipment failures, maintenance related, maybe, after they did the maintenance, they didn't put it back properly, human errors. And then, in some cases, accidentally, hydrogen was produced and people didn't realize it. So they thought there's nothing there, but when they light up something, there was residual hydrogen somewhere that they didn't know, and then because of that accident. So during the post-mortem, they found these reasons why industrial accidents occurred. And then sometimes, the failures are exaggerated out of proportion as something new that happened. As you can see, like I said, now from 1970, we have been using hydrogen in petroleum refineries, and they've been safely used. There are a lot of safety records. We talk about, safety record, several million man-hours of safety records of refineries. And there are a lot of industry codes, standards that exist even today, and more in the making, because, now whatever we talked about is all in the industrial environment, inside the refinery, inside the petrochemical, one particular area. But now we are talking about now bringing that hydrogen to our car, to our homes. That is where, more codes and standards and, safety aspects need to be considered, and there are more in the making. How do we reduce the risk? We all know, hydrogen is a highly inflammable one. So how do we reduce the risk? All the stakeholders, when I say stakeholders, the industry people, the academics and research scholars like yourselves, and then, investors, business people, we need money to work on these things, right? They all work together to learn and improve this quickly because time is running out. We all heard, that the COP28, we all agreed, that 1.5 degree Celsius temperature increase is the max that we can tolerate in order to make sure our sea levels don't rise. Many island nations will disappear. My own country, Singapore, may be at danger. Cross-country and international collaboration. Cross-industry and international collaboration. Just not, So maybe now, we never talked before. Now, maybe the refining industry and automotive industry have to talk. Maybe the steel industry and the refrigeration industry may have to talk now. So cross industry and international collaboration. Just not we are no longer a regional player. We are a global player now. What happens in one country may affect the entire globe. We all know, about, the ongoing, conflict in Ukraine. We all know what is happening in the Middle East region. Something happening somewhere, things can get disturbed. Just, to highlight the properties, yesterday, I think the day before also, people highlighted the properties of hydrogen. I just want to bring, just 2-3 items there. It is the highest energy mass, energy per mass of any fuel. If you take any fuel in the, in the world today, and if you use, in per mass basis, if you burn 1 kilogram of hydrogen, you'll get the highest energy from it compared to any other 1 kilogram of fuel, petrol, methane, whatever it is. Okay. And then the challenge is, it has got a very low molecular weight, very low density. And because of that, for that 1 kilogram of hydrogen, you need several thousand liters volume, and that's a challenge. Yeah, just go back one more time. Okay, so these are, so I just want to explain, in the hydrogen, again, the industry has classified the hydrogen into different color codes based on, from where they are getting this hydrogen. So I'll start with, let me pick up my laser pointer here. So you can see my laser pointer, okay? So if the hydrogen is produced from natural gas as the feedstock, and then if you don't do anything with regard to, the carbon dioxide that is being co-produced, natural gas is methane, CH4. When you burn or when you reform it, it produces carbon dioxide and hydrogen. And if we let the carbon dioxide go into atmosphere, it is classified as a gray hydrogen. It's still a hydrogen, but you did not do something good with the carbon dioxide that you produce along with it, and therefore it is given as a gray hydrogen name. If you do something and capture that carbon dioxide, don't release it to atmosphere, and you repurpose that carbon dioxide, either you use it to convert it to another chemical, don't release it to atmosphere, you made another chemical out of it, or you buried it underneath, you buried it somewhere so it doesn't come into atmosphere, then it is given blue hydrogen name. Okay, same thing, you can also make hydrogen by gasification process from coal. So if you don't do anything and release that during gasification also, you will get some carbon dioxide. If you don't do anything to the carbon dioxide, it is classified as a brown hydrogen. But if you again do carbon capture the carbon dioxide or carbon monoxide that you are producing and convert that hydrogen, it is called as blue hydrogen. Okay, that's what. And then there is, if you are using nuclear energy, and then from the nuclear power, if you are doing an electrolysis process and then producing hydrogen, that is given a purple hydrogen category. The green hydrogen is what we'll talk more about in subsequent slides. Now, if you're using renewable energy like wind, solar, hydro, all these energies, if you're producing electricity from these sources and then do an electrolysis process, split water, H2O into hydrogen and oxygen, that hydrogen gets the name or the label called green hydrogen. And then, turquoise hydrogen, again, industrial process, we have been producing the steam methane reforming. SMR stands for steam methane reforming. Natural gas is predominantly, methane, and therefore it's, so there is, steam reforming process. And this steam reforming process is not something new. It has been existing forever. The SPIC fertilizer plant that I work for, and I'm so glad that my ex-boss is also on this call, Mr. P. Tyagarajan. We both worked in the fertilizer plant, and then, we steam reform naphtha, hydrocarbon naphtha, and then we produce hydrogen and we produce ammonia from there, right? So, so steam reform is nothing new, it's a regular industrial process. And so if you produce hydrogen through that, it is called turquoise hydrogen. And then, you can also take electricity from the grid, from our TNEB grid or, Maharashtra electricity grid, Gujarat electricity grid. Now, if you take from the grid and then you can do electrolysis and convert water to hydrogen, it gets a yellow. So anyway, they're all hydrogen. All this is, to make sure that everybody who is using the other way of producing hydrogen, need to find a way to come to that green label. How do we do that? So that's the different category of hydrogen. And then hydrogen can be transported by different means. I show here pipeline. They can be moved by trucks, tube trailers, as we call them, in a compressed gaseous form. They can be cooled as liquid hydrogen, and then the liquid hydrogen can be transported by sea, from continent to continent. And then on the other side, if it's a liquid, you evaporate it back and then get it as a gaseous function. Then you can again use it. You can use it in all these functions. One of the things that we'll talk in subsequent slides, how do we blend hydrogen with natural gas, and if we do that, what is the benefit? Okay. And then, these are direct, we talked, yesterday's speaker from Reliance, he talked about, hydrogen as a fuel for transportation. They can be used, for other industrial purposes. And then we are talking about, even bringing to residential, places, homes and residential places. Okay, if we do that, what happens? Yesterday's speaker also highlighted this one. Hydrogen flame is invisible. You can't see it. So if you're going to give hydrogen as a fuel to your kitchen, you academics and scholars, you can do research on, hey, how do I make this flame visible? By adding some additive. For example, right? Methane, when it burns, there is a blue color flame, right? So can I add a small dosage of methane or propane or pentane, whatever, I don't know what they know. Something that I can add to this hydrogen, so that when the hydrogen is used as a fuel in the home kitchen, the flame is no longer invisible. There is some visibility. There is some color to it. So that will be an area of interest for people, who want to, invest their, knowledge and money and time to find that out. Now, when it is getting commercialized, not today, maybe 5 years, 10 years later, then, you have a solution for it. So these are the avenues that I will touch upon in the subsequent slides as well. Now, where are these research opportunities for academics and scholars like yourself? Okay, this we talked about. Okay, here's a quick comparison, because we're talking about natural gas being replaced by hydrogen, not fully, but partially. Okay. So here is a comparison, I won't go through a lot into it. If I'm going to be using hydrogen in place of natural gas, as you can see, here's like a standard cubic meter. SCM means, standard cubic meter. And here the same thing, right? So as you can see, for 1 standard cubic meter, if I use today methane, I'm able to generate almost 30, megajoules of heat energy, right? 40 megajoules of heat energy. If I substitute the same by 1 standard cubic meter of hydrogen, I'll only be getting like 13 megajoules, right? And that means, it is 1/3, smaller heating value if I do some volumetric, okay? But we know, the molecular weight is only 2, molecular weight of natural gas 16. That means, if I do a mass, it'll go 8 times, right? If I have the, same mass, right? That means that I need to match, every 1 molecule of natural gas, I need to provide 8 molecules of, hydrogen. When I do that, I multiply this by 8. What happens? It is over 100. The heating value, becomes now more than 100 megajoules. And therefore, it has got the highest, from a mass perspective, But the thing is, we are transporting natural gas today by pipeline. And then the pipeline has been designed to carry certain cubic meter of gas. If I'm going to use the same pipeline and put hydrogen in it, either partially or, fully, then, I need to, how do I pass 3 times more flow? Not possible, right? The velocity will increase, okay? The velocity of gas will increase. So how that velocity increase is going to impact my pipeline structure is something, that the academics and research scholars like yourselves can work on. It is also one of the points I highlighted in my summary slide, but I thought I'll just mention it here. And both hydrogen and natural gas are odorless, colorless, no smell. If they leak, you can't find it. So today we chemically inject what is called odorant, it's a chemical in small ppm level, so that, when they leak, you can smell it and identify there is a leak. That's why, same thing happens to the LPG when you use LPG at your home. If the burner is not lighted on and if the gas is leaking, you can immediately smell something like a pungent, rotten egg smell. That's actually because a odorant has been purposely injected into that LPG. Likewise, there are studies underway, and yesterday also I mentioned that, underway, to add odorants and see, if you're going to take this hydrogen to your home kitchen, if it is leaking, how do you find it out? It is flameless. The flame is invisible. And then if it is also not smelling, how do you know there is a hydrogen leak, right? So there should be something from a safety standpoint to do that. So people are working on, identifying the right odorant that can be mixed with hydrogen. If there is a leak, people can sense it. A lot of trials going on. Okay. As a quick summary here, so it is so small, it can leak through, it can permeate through many substances. Maybe because of the molecular size, natural gas cannot permeate, but hydrogen can easily permeate. So when I convert this one, the concern is, if I'm going to inject a small percentage of hydrogen into the natural gas system, will that permeate through the substance and cause hazards to the society? So that's a concern. So now, this is a very simple chart, on the green hydrogen. So it has to be a renewable energy source, either wind, solar, or hydro, all of them are acceptable. You can use an electrolysis process, split the water into hydrogen, oxygen, and then the hydrogen is classified as and then you can use it for any other purpose. And then a bit on the electrolysis, process. There are a lot of electrolyzer manufacturers in the world, and a lot of companies in India have signed up for it, with some foreign collaborations and stuff like that. Okay, so they all have their own pros and cons. Alkaline electrolysis was the predominant one that has been existing for many, many, many years, and they use a liquid electrolyte, and then, they were using electrodes to, split the hydrogen and oxygen, and they've been using it, very popular. But this one is not, per kg, produce hydrogen, today it is not very attractive. Okay. And then, and so yesterday the Reliance speaker also mentioned about this polymer electrolyte membrane, type, PEM. So it's gaining popularity. Most electrolyzer manufacturers today are getting into this one. And these are the operating ranges you can see, But you see on the far right, this is gaining a lot of popularity, but the biggest challenge is, it can only operate at a very high temperature. 700 to 1000 degrees centigrade, very high temperature, So only at this temperature, the split takes place, it can be split, and therefore, so instead of using here, use like, water, or, it is like alkaline water or, acidic water in these electrolyzers. But here, we use steam, it's same H2O, but you cannot send like a liquid water. You have to generate steam, and then that steam, when it goes, that then it gets split. So these are the technologies that are available, and again, there is no end to it. If somebody can come out with a new breakthrough invention of finding another electrolyzer, that doesn't use any one of these four, but something more unique, and then operate at ambient temperatures, and then it can produce pure hydrogen, then that is an area of interest. So there is no shortage of space for new inventions in the electrolyzer technology as well. This chart will give you a scenario of how big a vessel you need to design if you want to carry 1 kg of hydrogen. You see here, 1 kg of hydrogen, if it is held at atmospheric pressure, 11,000 liters. 11,000 liters, huge truck. And then, if you convert that 1 kilogram, of hydrogen into ammonia, of course, you're adding another component, nitrogen, it becomes ammonia. And if it's liquefied, if it becomes in the form of ammonia, it will get, sorry, it's again gaseous ammonia, sorry, gaseous, okay? It will occupy 1,400 liters. And then if we compress that, if we compress that 1 kg of hydrogen to 700 bar, 700 atmospheric, 1 atmosphere, is 1 bar, 700 times. Then you are able to bring it down to, 24 liters. But remember, to make a vessel or a tank or a cylinder to withstand 700 bar, you probably will have to use 700 kilogram of steel if you want to make it in steel. So heavy to carry just 1 kg of hydrogen, So that's how heavy it is going to be. And then if you liquefy it, if you liquefy 1 kilogram of hydrogen, you know that water, right? If you convert, if you take 1 kilogram water, just 1 liter, So if you convert 1 kilogram of hydrogen to liquid, it will occupy 14 liters. You need a pretty big, vessel to carry just 1 kilogram of hydrogen. And here's a quick comparison today, right? Most of us are used to using diesel, okay? So if you want to generate, say like a diesel genset or something, if you want to generate like a 84 kilowatt hour of, energy, you need only 8 liters of diesel. To generate the same thing, you see here, I need only 2.5 kg of H2. Here I need 6.8 kg of diesel, but here I need only 2.5 kg of H2. But you know what? I can't use like a jerry can and then go to petrol or diesel pump and collect 8 liters of diesel, right? I have to carry a 61 liters, and that cylinder will weigh, just to carry 2.5 kilo of hydrogen, the weight of the cylinder is 44 kg. And then you see 70 MPa megapascal, 70 megapascal equals to 700 bar, and therefore, to make a vessel of 61 liters worth withstanding 700 bar pressure, the weight of the cylinder is 44 kg. And then this is the, we call the, the load carrier, right? The load is only 2.5 kg, but my carrier is 44 kg. So that's how the comparison, because of the low density of the gas. These are the challenges, okay? So these are, the storage options that we have in front of us, physical storage, if it is at 1 bar pressure, how much is the density, and as I increase the pressure, 150 bar in the bar, so you can read it, So the comparison is, reference point is, water also contains hydrogen. It is a liquid form. So in the liquid form, in 1 liter of water, we can get 111 grams of hydrogen. But in all of this, you see, some are like, these hydrates, they can go up to like 150 grams, but many of them, can only capture a very small amount of hydrogen. So that's a challenge. Okay. These are the transportation and storage facility available today. Pipelines, like I told you, there are a lot of pipelines existing in US, in Europe, elsewhere, hydrogen pipeline, some are in the construction, some are already operating. Like I told you, there's a 240 kilometer of pipeline that has been operating since 1938 in Germany. It's not something new, okay? So, these are the, pictures I gathered from, the internet, these are the sources, where I got this from. And these are the pictures of, tube trailers, they can transport, but the, air products, and they're producing hydrogen, see, these are huge truck. But if you look at, what's the weight of hydrogen that is going in this truck, probably 10 kilogram, probably 20 kilogram, something like that, very huge truck. These are like a liquefied hydrogen stored in a Horton sphere, very popular, and then the temperature we are talking, if it is an atmospheric pressure, the temperature is negative 253 degrees centigrade. Yesterday, the Reliance speaker also mentioned that. So at a very cold temperature, and these are, liquid hydrogen ships, transporting from continent to continent. There was a shipment of liquid hydrogen, transporter from Australia to Japan, when the plant was commissioned, middle of last year, and then, these are, cylinders that are stored, hydrogen cylinders that are stored in a factory, and then these again, hydrogen transported by trucks, liquid hydrogen transported by trucks, within the country. They exist today, nothing new, they exist today, but, it is not, it's not economical, they're doing it because they're doing a lot of trial and error to see, where is the, optimal, price and stuff like that. But, they exist today. Okay. And yesterday, the speaker also talked about, the type of cylinders, type 1, type 2, type 3, all metal, some are, with the, he talked about carbon fiber, right? So here are the, the ones that are lightweight, So type 5 is all composite, no metal at all. So this is, this is the best thing that can ever happen if they can find a composite material that can withstand that 700 bar, 1000 bar pressure, but made of composite material, lightweight, then yes, this will be viable. But today, I think type 3 and type 4 are the popular one. They still have some liners. The outer is like a composite material, but internally there is either a plastic liner or a metal liner, so that, the hydrogen does not permeate. So any composite material that you develop has to withstand the pressure, the mechanical strength, also the permeability. It should not allow hydrogen to escape. Okay. So, I took this from one of those, cylinder manufacturers today. Okay. And then other options people are exploring. A lot of pilot programs are going on, they want to pump hydrogen that is produced in excess and store it in salt caverns or even, depleted oil and gas fields or, aquifers, So these are all, underground storages, people are exploring that. A lot of investment has been pumped in by European countries, America, not sure about India though, So there are a lot of, people are thinking, if I have excess hydrogen that I cannot use immediately, where can I store? Okay, so people are, thinking along these lines. We talked about compressed hydrogen. There are up to 1000 bar storage facilities. As you can see here, people store these in this tube, tubular form, storage, and they're all interconnected. A lot of safety valves and safety checks, measurements go in this one. Not easy, but doable. So these are existing today. In the compressed gaseous storage form. Okay. And we talked about the liquid, at atmospheric pressure, it is at minus 253 degrees centigrade, very, very cold. You need special material handling, safety, all of that around that. Okay. Okay. And then, the chemical form. Okay. This is something very interesting. Okay. So like I told you, ammonia is not something new. Ammonia has been there forever. So ammonia is produced from hydrogen and nitrogen. Nitrogen we get from air. And hydrogen we can get it from many processes like you saw before. So the countries like Saudi Arabia, Abu Dhabi, Dubai, Australia, where they got abundant solar power, maybe not wind and geothermal, but they got abundant, solar power. So they want to install mega size solar power plants, generate electricity. From the electricity, electrolyze water, produce hydrogen, and then from air get nitrogen. They can liquefy, air and then separate nitrogen, mix nitrogen and hydrogen, make synthesize ammonia, and then export ammonia. Even today, countries like Saudi Arabia, Qatar, Oman, all these countries, they are actually manufacturing ammonia and exporting more for fertilizer purposes. But in future, people are talking about, can ammonia be used as a fuel? The answer is yes. A lot of research is underway. They're talking about fuel cells that can take ammonia. They're talking about combustion engines using ammonia. Of course, ammonia is a feedstock for fertilizer and many other industries. But can they, use ammonia as a fuel for ship engines? instead of using diesel or, the bunker oil, So there's a lot of research going on. There's a future. A lot of trials are happening across the globe. Many countries, many companies, corporations are investing in this area. Okay, so hydrogen stored in a chemical form, mainly ammonia, existing today. So it's not something totally new. Whereas and transport ammonia is very easy because ammonia can be liquefied and the temperature is minus 33 degrees at atmospheric pressure, and therefore it can be transported in the sea, and it's been done before. Like LNG, some of you may be familiar with LNG, liquefied natural gas. Natural gas can be liquefied, and then it becomes a liquid at like a minus 190 degrees centigrade, and then liquid natural gas, LNG, has been transported across the globe from continent to continent. It's been going on forever, and therefore ammonia can be easily transported. And then if ammonia can be used as a fuel, well and good. The only concern would be there's a nitrogen, right? So at high temperature, when hydrogen burns, no harm. Hydrogen becomes moisture, steam, and gets out. But at the same temperature, when nitrogen gets burned, you'll get nitrous oxide. So you need technology to make sure that nitrogen oxides are limited. So there's a technology, there's a research underway to make sure that the nitrous oxide generation is minimized. Okay, yeah. Another process is, yes, convert the liquid ammonia. You can store it, and then we can crack ammonia. It's a reversal process, right? You synthesize ammonia. It is a catalytic reaction, exothermic reaction, and you produce ammonia. And likewise, at high temperature, using a different catalyst, you can crack ammonia and become nitrogen and hydrogen. Okay, and then it is not something new. It has been there forever. In fact, in the SPIC fertilizer plant where we work, we had a small nitrogen generation unit. And I was thinking, hey, nitrogen generation unit from where? They are actually cracking ammonia. We are producing ammonia in the plant. They are cracking ammonia in a catalytic vessel, and then they were generating nitrogen. And nitrogen is a utility required for all these, chemical and petrochemical plants for purging, for inert purging, So you can't, every petrochemical refinery plant will have one nitrogen generation area. Either they separate the nitrogen from air using air liquefaction process, or something like, we had ammonia in the plant, and therefore instead of putting an air liquefaction plant, they had used the nitrogen, crack it, they crack ammonia, and then, so it is there. So at the point of use, you can transport until the point of use in the ammonia form, liquid form, and then you crack it, and then use it, at that point, hydrogen. And you can release the nitrogen to atmosphere. Today, a lot of things are happening in small scale, but in the large scale, people are thinking about it, nitrogen cracking, and then you have to do some purification. Okay, and then I think I touched upon this one, a lot of metal hydrates, absorbents, and carbon-based material and chemicals. Of course, they're also talking about, ammonia, borane, borohydrates, all of this, I'm not a chemical engineer, so I kind of took this information from the websites, make sure that a lot of research is happening, a lot of pilot programs are happening in this area, because some of them, they can be stored at lower temperatures, but some of them they need a very high temperature to store and then also to regenerate. If you want to release the hydrogen, you still have to raise the temperature. So therefore, is it economically viable? So that's the kind of, technology revolution taking place. Okay, this is something, very close to my heart because I am involved in this one in my job as well. I was involved in my job in this one, where we produce hydrogen. And then there is existing network of natural gas transmission and distribution. Even in India, natural gas has become a primary fuel for homes and industries. And therefore, a lot of natural gas transmission and distribution take place. So the industry has identified an opportunity to replace a part of natural gas, blend hydrogen with natural gas. And current limit is, we are talking about 20% of hydrogen mixed with natural gas. So it means the balance 80% will be methane in the mixture. So they say if you do that, existing natural gas network, the pipes, homes, utensil, all the equipment that use natural gas as the fuel, they can all tolerate this one. When you add 20% by volume, not by weight, okay, not by weight, no, 20% by volume. If you add that, that means you can substitute that, and that will actually reduce the amount of carbon that is being released. Instead of burning 100% by volume of natural gas, now you're only burning 80% of volume by natural gas. The balance 20% by volume is hydrogen, and hydrogen doesn't release any carbon dioxide, and therefore there'll be reduction in the carbon dioxide emission into atmosphere. So that's the thinking. Okay. So you can produce clean hydrogen using green hydrogen methods, and then inject that into the pipeline, and therefore you can achieve this is a transition phase, and therefore you can achieve carbon footprint reduction. So this is called now power to gas. That means you produce power from renewable energy sources, solar and wind, and then from the power you generate hydrogen electrolysis process, and then you get that gas and then you convert it. And they're also talking about there is millions of kilometers of natural gas pipelines if we add up all the pipelines throughout the globe. So if you produce hydrogen this way, yesterday the speaker was talking, right? Hey, wind is available only at some time, solar is available only at some time, maybe if the consumption is not there, if you produce excess power, how do I store it? I need a lot of battery power, right? And if battery power is not available in mega scale, in small scale, yes. So how do I do? They said, don't worry, generate as much renewable power as you can from wind, from solar. Use electrolysis, make hydrogen, pump it into the natural gas system. And natural gas network, the pipeline, the millions of kilometers of pipeline in all the continent, they all have storage capacity. Store it in them. And then you can either use it as a blend, one option, or at the other point, you put a pressure swing absorber or membrane separation, and then you separate natural gas and and hydrogen. So there are a lot of membrane technologies available where the blended hydrogen and natural gas can be again separated through membrane separation. So that technology is also available. So you can use it as a blended gas. So carbon footprint will come down. Also, if you want pure hydrogen, now you pump hydrogen from one area and then let it travel in the pipeline, go to another city. There you put a membrane separator and then separate out the hydrogen if you want. Okay, so that is the technology they're talking about. Okay. Yeah. So I think a lot of prior speakers who came before me, they talked about this one now. So I talked about a blending of hydrogen, which we have done before. This is my sweet spot. Where we have supplied natural gas grids blended with hydrogen. I'll show you a photograph in a moment. Okay. So hydrogen comes here, natural gas comes here, and the blended gas goes out here. Okay. So very commonly available. And there are a lot of fuel cell, power plant, so many, stacks of fuel cells, it's a real picture, where, so many fuel cells, they generate power, and then we talked about now hydrogen fuel cell vehicles, nothing new, but, a lot of research is underway in this area. And then, a lot of companies like Siemens, GE, they are all investing into, can we use hydrogen, 100% hydrogen as a fuel for the gas turbines, So here's I think they're doing a pilot program, So this is how they're doing it, from wind and from renewable energy. They want to electrolyze, create hydrogen, store it, and then use it. So they will have dual fuel, They can use natural gas, they can blend it with hydrogen, or when there is enough hydrogen available and the turbine is ready to accept 100% hydrogen, they can actually switch to the full 100% hydrogen mode. So there is about 12 megawatt capacity. It is under construction, and these are the hydrogen fuel internal combustion engines. These are fuel cell based, but these are the fuel cell. So there's a lot of research going on around this area. Okay, so here is a real, a story. I'm in Canada right now, and this happened not today, but this happened 2 years ago. So there is a blending station. As you can see, the home of North America's first hydrogen blending facility and power to gas plant. Okay, so Emerson, the company that I work for, is the one who helped the customer to install this one. So this kit that you see here and this cubicle that you see is all done by Emerson and its business partners, based in I'm in the city Toronto, and this site is in a place called Markham, which is about 30-40 kilometers from Toronto, not too far from where I live at the moment. So very simple schematic here. There's a natural gas inlet, there's a hydrogen inlet. Here is the mixing area, the blending area, and then the blended gas comes out, and then the blended gas has to be injected into the network. And therefore, now you need a pressure regulating station to make sure the blend takes place properly. There's no backflow from the pipeline into this blending station, right? So you got to make protection, safety protection in that way to make sure there's no backflow. So these are a real life example. It has been operating for almost like 3 years now, and this consists of all this equipment. Okay, and then this is another success story for us. In Emerson, we supply 100% hydrogen fuel gas. A skid. This is a skid that you see. Entire thing is stainless steel pipe, as you can see here. Customer requested us to do the stainless steel piping. So we did that. This was also delivered a year ago, more than a year ago. And it is for a green steel plant. There's a company called Bauer Steel. A huge steel company in China, and they signed up for converting their entire steel plant to become a green steel, meaning they will not use coal, they will not use fuel oil, they will not use natural gas for their furnaces. They'll convert everything to hydrogen. So they have started in a pilot way, and it's not fully converted yet, but that's it's like a 5-year program that they signed up for, and then we supplied that skid, and it has been working for the last year and a half. Okay. So I think my earlier speakers also touched upon this one. So there are some concerns about materials compatibility for hydrogen, because hydrogen induces embrittlement, and therefore, and then it doesn't happen in one particular environment. It's like it is called hydrogen environment embrittlement. And what's that environment? Environment can be pressure, temperature, concentration, many things. You see, pressure, hydrogen concentration, temperature. And then other impurity. Sometimes some other impurity present in the mixture is actually helping not to progress the embrittlement. We had these situations. So these are all studies done. And then they affect the mechanical property and all these. So there is a lot of study, and Emerson got involved in that because we are participating in this hydrogen field. And these are some of our products under testing. This is a diaphragm of a product, of a regulator product, that is being tested. Because the diaphragm is made of rubber, and then hydrogen can permeate through that. Okay, so we do that. And these are some of the nuts and bolts that go inside the product. So we got to make sure that they don't fail because of embrittlement. I got some more photographs to show. Okay, so these are like soak testing. That means we soak these components inside these small chambers. Different concentration. 5% hydrogen balanced natural gas, 10% hydrogen balanced natural gas, 20%. So we kind of do all of that blends and put our screws, our springs, our nuts, our bolts, and then soak them. Some are soaked for 1 week, some are soaked for 4 weeks, some are soaked for 6 weeks, some are soaked for 6 months. And then at periodic intervals, we take them out and test them. Subject, is the time duration, the longer it is soaked, does it get different embrittlement? Or after some time, it is saturated, no more embrittlement progressing. So we do all of that study. So these are all some of those, study that was done in-house and also using third-party, testing facilities. You see some of our products, all these, springs and materials, elastomers, elastomers also, go through this one because there is a phenomena called explosive decompression. What it means is, all these rubber components, they got minute porosities. And then even natural gas, its molecular weight is 16, 17, 18. It can permeate through those pores and stay inside the pores at high pressure. Now, the pressure may be 50 bar, 60 bar. The high pressure gas permeates through the pores and stays inside the elastomer. And then when the product gets depressurized, maybe for overhauling, servicing, when it depresses, what happens? The gas that went in is unable to come out. It's like a non-return valve, check valve. It is unable to come in. So what happens? Outside, you're depressurized, but the gas is entrapped inside that O-ring or the gasket or the diaphragm. It develops blisters and cracks, and then when they remove it, they'll find hey, this O-ring is damaged. Actually, what happened was the O-ring did not get damaged in service. The O-ring got damaged because of this explosive decompression. So this is a phenomenon. So a lot of these elastomers will undergo this type of a testing. And then after my product is fully assembled, I want to make sure in every joint, there are a lot of joints here, right? Is the gas permeating, leaking through this one? So we use like these sniffers, to detect leak. We of course we put it in the water bath and see if there any bubbling. In addition to that, because sometimes the bubbling may not be able to sense it. Maybe it is too small and then naked eye cannot detect it. But sniffers can detect, even if 1-2 molecules of hydrogen escape, it can sense it. So we do all this testing, very, very intensive testing lasting like 3-4 years to do that. Okay. So here is like a summary slide on the hydrogen space for academics like yourselves and scholars like yourselves. Okay. Hydrogen fuel internal combustion engine. We talked about material for high pressure gas storage, like a lightweight, high strength, prevent permeation, blah blah. We talked about this rapid gas decompression, or RGD as they call it. So it should not explosive decompression should not happen. Okay. And then I talked about hydrogen leak and flame reduction. How do you do that? It is an invisible flame, and how do we do that? So you could collaborate with national, international codes and standards organization and see because a lot of new standards are being developed. So you could contribute based on your research and your findings. Collaborate with industries, people like like Reliance, for example, Adani, for example, L&T, for example, because they're also involved in this type of projects, and then you can write industry standards. And something that I came across in my work, velocity limits. Today, what happens, for the natural gas pipeline, there is a velocity limit. Before filtration, the velocity in the pipeline of natural gas should be limited to 20 meters per second. After filtration, the velocity can go up to 40 meters per second. So when we design a natural gas kit, for example, I have to make sure before my filter, my pipeline should be designed for, not to exceed 20 meters per second at the maximum flow condition. And same thing, after the filtration, I should design a pipe not to exceed that 40 meters per second. Now, when we inject hydrogen into this, blending of hydrogen with natural gas, if I do the same limit, is it the right limit or is it not the right limit? Okay, so a lot of research is missing in that area. Today they are just following the natural gas specification, but is it the right? We don't know yet. And then very important thing is called stratification of hydrogen in blended gas. What is stratification? Stratification is a phenomena that happens. It's like when you mix water and oil floats because of specific gravity, right? Very similar. So when I'm mixing natural gas with hydrogen, we think it is going to be a homogeneous mix. It may be a homogeneous mix. It may be a non-homogeneous mix. We don't know yet. We think there is some stratification, especially if the velocity in the pipeline is very small. And also if there is a storage tank, for example, I blended hydrogen with natural gas and I just stored it. It's a static tank. So we think all the hydrogen will go up and stay on the top, and all the natural gas will stay at the bottom because of the density difference. That is called stratification. If that happens, then this material may be subjected to unnecessary stress, because the pipe is made of one material, but if there is a higher concentration of hydrogen on the top and lower concentration of hydrogen, am I going to experience embrittlement on the top surface? So especially, let's say this joint here, for example, hey, will this joint undergo embrittlement because it is on the top, and therefore, is it susceptible for potential for more damage, more crack? So these are the study. So these are the key concerns. And so the factors are many. How do we inject? If we inject vertically, we inject horizontally, inject from bottom. So a lot of things can happen in the shape of the pipe. If the pipe is straight, if the pipe is tortuous. So all the pipe geometry. So all of that. So today we follow a rule of thumb that we add static mixtures. And after I blend it, I add a static mixture so that the gas cannot travel straight. It can go to bend in a tortuous manner. With that, we are able to ensure. So when the gas is flowing in the pipeline, we can ensure that. But there is no guideline today in a stored vessel. I told you, right? We are transporting blended natural gas and hydrogen in high pressure tanks. So when they're transported like a CNG, trucks, and if I have mixed hydrogen with it, if I'm going to transport that truck on the road, will the hydrogen go and accumulate on the top of that tubular truck, and then will it affect the lifetime of that tubes over time? So that is something the scholars, you people can look into that, and then study and then give your findings. So now I move on to this biomethane. Mr. Dr. Chinnapandian, I think overrunning my time. Can I take a few more minutes?
Yes, sir. Excellent speaker has come, sir. Second speaker has come. Yeah. Yes, sir. Yes.
Okay.
For 5 minutes.
Okay. Thank you. Okay. So the biomethane, is also called as, renewable natural gas. Okay. So, in some literature, in some, websites, you may find this word RNG. That's why I put it here. Okay. So basically, they are using the biomass to generate this biogas. And, it's not something new, right? I'm not sure how many of you are very familiar. When I was a little boy and I went to my village, my grandparents' village, I saw this Gobar gas plant. It was existing in 1960s and 1970s. Nothing new. We have done it before. They take the cow dung, mix it with water, put it in the tank. There is a float here. There's like a cylinder which is inverted, and gas gets accumulated. But this is got methane, carbon dioxide, and plus some unwanted stuff. But we only want methane. So we take it to the kitchen, and there was a stove there, and then we could use it to cook food, or you can even put lights. We can use the the gas lamp. Those villages where they didn't have electricity, they were able to use this to burn the lights. It was all there. It's not nothing new. These are called the micro biogas plants. And there are millions of them throughout the world. Many countries. It's not nothing new. But now we are commercializing it. Okay, huge corporations are investing in such biogas plants. They get all this stuff from different sources, and then they digest it and produce biogas. So biogas has got methane plus also unwanted stuff like carbon dioxide, other stuff, and then they got to they can burn the biogas straight away, or they can upgrade it. Upgrade it means remove all the unwanted impurities. When they remove all the unwanted impurities and then get a good concentration of biomethane, 95, 99% biomethane, then it is given a name called biomethane. That biomethane can substitute the natural gas that we are deriving from the Mother Earth, from the oil and gas wells. Instead of the fossil fuel natural gas, you can replenish it with the biomethane produced from bio-waste. Okay, so there's a concept here. Okay, and there are a lot of standards, written around. These are mainly European standards, written around that. And Europe has made a commitment that all the existing utility companies which are using natural gas has to have that much amount of biomethane injected into the network, and these standards are governing that. Okay, so this is something that is existing, already. And then this is some of our biomethane injection skids. That means we install these skids in the biomethane producer side, and then it is also for billing purposes, right? There is a buyer-seller agreement. Biomethane producer is one. The natural gas distribution company is different. So you got have the so all this one, and then before you inject it, we have to make sure that the biomethane that was produced meets the specifications of the pipeline. If the pipeline has got 90% methane and your biomethane that you produce has got only 80%, by injecting that lower concentration of biomethane, you are diluting the entire network, which is not allowed. And therefore, you got to make like chromatographs and stuff like that to measure that the quality of the gas that you produce in the biomethane is of good quality, meeting the product specification before injecting it. And otherwise, you also want to prevent backflow. From the natural gas grid, you should not get the flow back into your injection skid. So all those safety protection systems are all featured in this one. So this is from Emerson. And here, these are biomethane powered power plants. Here I put like, a combustion, like a combined cycle power plant that is using biomethane or biogas as the fuel for the plant. And this is how it looks like. They produce biomethane. They can inject it into the natural gas. They cannot inject biogas into natural gas straight away because biogas has got a lot of carbon dioxide, right? So it's no value. It has got a lower heating value, so they cannot do that. So if they want to inject into the existing natural gas system, they got to convert the biomethane. But they're going to use like this called heat and power plant, combined heat and power plant. So they can use the biogas and then they can produce electricity. And here you see, the biomethane trucks and buses, operating in many countries. I took these pictures from some European sites. Okay, so these again, these are the internals of how the station looks like for the biomethane. They have all this equipment inside. Some pictures of the interior of that cubicle. Yeah, so these are the operators' challenges. What are they? So they have to comply to the local standards and legislation. They got to be safe, and then there should be an accurate buyer-seller billing. Because the biomethane seller gets billed or is billing the buyer of the gas, and then if there is inaccuracy, somebody is losing money, right? So so we have done it today. We have Italy and France are the two countries that are very advanced in this area. And then the research opportunities for you academics and the purification process can be still optimized. There's a lot of scope for that. And then, like I said, right, the biogas has got a lot of carbon dioxide. So how do we capture the carbon dioxide in that, and how do we dispose that? How do we repurpose it? Where can we repurpose it? If you just release it to atmosphere, yes, you did a good job on biomethane production, but you release the carbon dioxide back to atmosphere. That means your carbon footprint did not come down. Okay, and then biogas production. Hey, can we use multiple feedstock? Agri farm, cattle waste, poultry, food waste, municipal waste. There are many organic waste around available. So can the biogas production accept multiple feedstock? Then another thing, there are many places, where the water is shortage, and this may be a water intensive process. So for water shortage areas, is there a way to optimize, the water consumption? Then wastewater management, because, when you do this biogas digestion, there is other waste, toxic waste that is coming out. So how can we, improve that? Is there an economical recycle where, the water shortage area, wastewater, can it be recycled? Can it be cleaned up and then reused? And then toxic waste, because there'll be some sulfide, there'll be others, that may be coming in the way. So how do we do the toxic waste management? So these are some research opportunities for academics and research scholars like yourselves. I think that brings me to the end of my session. I'm sorry, I had to rush towards the end because we started a little bit late, but I hope, my pace was okay and you were able to follow my speech. Stop sharing now.
Yeah, any questions from participants?
Yeah, like I said, no, I cannot see the chat here. So, you have to read out if there are any questions in the chat, you please read it out for me. Or,
Yes, sir.
if they want to, unmute and then speak, that's fine too.
Sir, good evening, sir.
Good evening.
Really wonderful presentation.
Thank
I
you.
am belong to chemistry department.
Okay.
Sir, this is the first time I'm hearing that ammonia may be used as a fuel.
Yes, it's a work in progress. Like I said, no, there are a lot of research going on, to use ammonia as a fuel in multiple areas. Yeah.
Sir, the ammonia gas may be used as a fuel cell setup or in combustion engine.
Both, in one of my slides, I think I show that. Okay, let me go back to that, which is that I'll show you. You see here, that they're thinking of, using, okay, you see, ammonia fuel cells, ammonia combustion engine, both.
Both.
Yeah.
So
there's a lot of research underway, to do that.
Okay, sir. Okay. Thank you, sir. Thank you.
Yeah. So, so this is, these are like, right now, right? These are like, a proprietary information, and not much information may be available, but there is study going on. And therefore, if your, research area allows you to do that, I think it is good looking into it. Again, from an India perspective, some of the technologies that are developed overseas may not be economical for the Indian, conditions, right? So you might be, able to find something that is unique for Indian environment.
Thank you, sir. Thank you.
Okay. Yeah. Most welcome.
Sir, there is some questions for the chat box. Sir, when
sure.
hydrogen is blended with natural gas and used, will it reduce carbon footprint?
Absolutely. So because, like I said, right, let's say, I've got 100 kilogram of hydrogen, 100 kilogram natural gas. I'm using it today. I'm going to just, remove 1 kilogram of natural gas and replace it by 1 kilogram of hydrogen. That means 99 kilogram is still natural gas, but 1 kilogram is now hydrogen. So when the 1 kilogram of hydrogen burns, it is not going to release any carbon dioxide, right? And therefore, there's a carbon footprint reduction. So yes, that's why, right now, the industry has come to kind of an alignment across the globe, up to 20% blend volume, because, they can't tell every home, right? If we're going to increase the hydrogen blend in the natural gas, so go and buy new stove, go and buy, not going to happen, right? It's going to take place in phases. And therefore, they say, if they inject up to 20% by volume, it will not change the heating value abruptly. It will not require change of equipment. It will not require change of any operating parameters. You just continue to do the same way, but you have reduced the number of methane molecules that are being burned. You replace them by hydrogen, and because of that, your carbon footprint will come down.
Yes.
I hope I answered the question.
There is some questions from my side, sir. So what about
Sure.
research in India, sir, about hydrogen technology? How is going on in India, sir?
Okay, I'm not aware of any major breakthrough research going on in India just for hydrogen, because hydrogen is not a new material. It has been there for many decades now. It's just that now how to bring this hydrogen as a reliable energy source to the domestic environment. Like can it be can be used as a fuel at home? Can be used as a fuel at the industries, at the steel plants, at the other, wherever currently they are using natural gas. So those are the area. I think there might be companies like Reliance, who are, we heard from the Reliance speaker yesterday. I think they are heavily investing in that area, So I think there is some research going on in India as well, but I don't have a lot of information right now around it. All I know is, all the countries, including India, they have formed a hydrogen association. Okay, So
Yes.
every country around the world has got a hydrogen association. So getting into that hydrogen association, participating in the hydrogen associations seminars and webinars, and getting a membership, will be an added advantage, for scholars and academics like yourself, to understand what those hydrogen associations are doing, because they are the probably the window to the government, and then through them they can say, hey, where is the investment happening, what are the gaps that are existing, and where are the areas where you can participate and fill the gap. That would be my way of approaching. So every country, including, for example, Singapore, they got a Singapore hydrogen association, and they're affiliated. So every country's hydrogen association affiliates with the international community, through collaboration and stuff like that. So I think that is one way of approaching this space.
Thank you, sir. Thank you, sir.
You're welcome. My pleasure.
Yeah, yes, sir. Yes, sir. Please, sir.
Okay. So I stopped
request-
sharing. Okay.
Yeah.
Stop sharing.
Yeah.
Okay, yeah.
Dear participants, please unmute your videos. Okay, sir. Thank you,
Yes.
sir.
Thank you so much.
Sir, thank you very much, sir. So I request
Thank you, sir.
Dr. Purushottam to give formal vote of thanks.
It's once again, it's a very great pleasure to express my sincere thanks to our speaker today, Mr. Ilangovan. I think he's elaborately explained about the hydrogen as well as natural gas, and also the new the future fuels we had today. Ammonia is the future fuel. Maybe it's also one of the resource for our future transportation or energy production in our world. So definitely the new research will start from ammonia and storage, production of ammonia and storing the ammonia also. As per my knowledge, we are having the ammonia in the vapor absorption system in a refrigeration condition. That also they are now eliminated. They are not using as per our Vice Chancellor inauguration speech. Okay, but maybe this ammonia you can use for any cold storage or anything. But in futures we can use as a fuel. So this is a more informative session today. We had a lot of the knowledge from your side, sir. Thanks once again. Thank you very much on behalf of our college and from participant and organizer and ACT, sir. Thank you very much, sir. Once again, thank you.
Thank you,
Thank
sir.
you very
Thank you,
much
sir.
for giving me
Thank
this opportunity. It is a pleasure. It's a honor. It's a pride for me to talk to. There are so many doctorates. Listen to me. I'm just a graduate. And I learned so many things from my experience, and it's a great honor for me. Thank you, Mr.
Thank you,
Dr.
sir.
CHINNAPANDIAN,
Yes.
for giving me this opportunity.
Thank you, sir. Thank you. Thank you, sir.
Thank you so much. Okay.
Thank you.
Okay.
Yes.
All
Thank
of
you,
you
sir.
have a good night. It's a late in the evening for you. Go have some dinner and get some good rest.
Yes. Thank you, sir. Thank you.
Thank you,
so
sir.
much.
Thank you, sir. Good night, sir.
Okay. I sign off now. Thank you.
Yes.